Assalamu alaikum warahmatullahi wabarakatuh. Welcome everybody. In this video we are going to talk about signal flow graph, which is an alternative to block diagram for representing control system. Previously we have studied the block diagram, and we said the block diagram usually consists of blocks, signals, summing junction, and pickup points. We also learn how to simplify the complicated block diagram into a single block diagram with a single transfer function by using the reduction techniques. In this video, we are going to focus more on signal flow graph as another method to represent the control system, which is preferred to represent the complicated or the complex control system. Usually, signal flow graph consists of branches that represent systems and nodes which represent the signals. So as we can see here, this is the branches which represent the system and node which is represent the signal. There will be interconnection between these nodes and branches. As we can see here, this is an example for signal flow graph. And this example we can see here, we have several nodes, roughly 7 nodes, and we have 6 branches. And there is a connection between nodes by using these branches, or which represent subsystems. So we have between R1 VS, R2 VS, R3 VS, there is 3 branches. Each branch represent one system, which is G1S, negative G2S, G3S. And also here we have another 3 subsystem which represented by 3 branches between node VS and node C1, C2, and C3. In order to simplify such signal flow graph into a single transfer function like we did before with the block diagram, we will not going to use any reduction techniques here, but we are going to use the flow graph gain formula, or we call it Mason's rule. So Mason's rule is a method to represent or to find the single transfer function of a complicated signal flow graph. So this signal flow graph, which consists of 6 subsystems here, can be represented by a single transfer function, as we will see later on. Before we go to learn how we are going to apply Mason's rule, we will learn some of the concept of signal flow graph. So previously we have mentioned about the topology of the block diagrams, and we said we have the cascade topology, we have the parallel topology, and the feedback topology here. So how we can convert this topology from block diagram form into signal flow graph. So for example here in this block diagram, we have 3 subsystems, G1, G2, G3. We have an input signal RS, we have an output signal CS. So in order to convert this block diagram into signal flow graph, we need to identify the nodes and branches for this block diagram. So how many nodes do we have? Actually, usually at least we have 2 nodes, one input node and one output node. In between, we call them the intermediate nodes here. So here we have RS, so we just draw one node, we call it RS. Then the other node is, we call it CS, or the output node. In between, we have also 2 nodes here. We have node which represent X2 here, we call it V2. We can call it X2, we can call it V2, any name for the variable here. And we have another node here, for X1, we call it V1. So in total, we have 4 nodes. After we define the node, we need to define the branches or the system between these 2 nodes, how these nodes are connected to each other. So for example, between node RS and node V2 here, we have one subsystem, we call it J1. So we draw a we draw branch between node RS to node V2, and the value here, or the gain, we call it G1S. Okay, then between this node and the other node here, after the system or the subsystem G2, we have also the gain will be G2. Then from this node to the output, we have another subsystem transfer function, which is J3. So here we have 3 branches, we have 4 nodes. So this will be the signal flow graph representation of the above cascade system. If we go to other system, which is the parallel form or the parallel topology of the block diagram here, As we studied before, this is the parallel topology. We have one input which is distributed into three subsystems, and we have one output here which is CS. We want to convert this block diagram into signal flow graph form. So we should first identify the nodes. So we have one node for the input here, we call it RS. Okay, one node for the output here at this summing junction, we call it CS. In between them, we have some subnodes, or we call it intermediate nodes. So we need to define this intermediate node. So we have one intermediate node here, one intermediate node here, one intermediate here. So we call it V1, V2, V3. You can call it X1, X2, X3, Y1, Y2, Y3, any variable here, just to identify or to name these nodes. Okay. After you draw these 5 nodes, we need to draw the branches between nodes that interconnect between the nodes. So from node RS here until the node here, we have one subsystem which is J1. So we just draw one branch from RS to V1 with the subsystem value which is J1. Then another branch from RS to V2, RS to V3. After we draw these 3 branches, we want to draw the output of this node, or the connection of this node to the output node. As we can see here, the input is come from RS, the output is go to the CS. Okay, so since there is no another subsystem, only we have G1, so this branches value or branches gain will be represented by 111. So whatever is the value here will be goes to the directly to the output. So the product of this J1 times 1 will give you J1. So between RS and CS we have only J1S. Here G2 times 1, so it will be G2. G3 times 1, it will be also G3. So nothing, this 1 just to identify or to highlight that we have nodes in the middle between these two, or between this the input and the output of our system, or of the parallel system. So you can see here, this will be the representation for this parallel block diagram. This is the third topology that we have, which is the feedback topology. And this is the block diagram of feedback topology, consists of the GS and the feedback HGS. In order to convert this block diagram into signal flow graph, we need to identify the nodes and also the branches. So the nodes here is represent the input node, which is RS, the output node, which is CS, and the intermediate node here is the summing junction, we call it ES. Okay, then we need to draw the line or the branches between the nodes, or to show interconnection between nodes. And we have between RS and ES here, there is no subsystems, no transfer function. We just draw it as a line with the gain of 1. Then between ES and CS we have one subsystem, one transfer function, which is GS. So we write it as GS here. And then the feedback loop, which is HS here, with the negative feedback. Since it's negative, so we put it negative HS here. We need to consider also the direction of arrow here. It's go from RS to ES, then from ES to CS. So this represents the signal flow graph representation of the feedback system block diagram that's showing in this figure. Now we have one example here, how we can convert a block diagram into a signal flow graph. So here we have a block diagram which consists of multiple subsystems for G1, G2, G3, 4, 5, 6, 7, 8. We have 8 subsystems here. So we need to convert this block diagram into a signal flow graph. So first we need to identify the location of the nodes. Then we need to draw the interconnection or the branches between nodes, which connect from one node to other node. For example, here we have some nodes which is very clear to be identified, like the nodes at this summing junction, and we have another node at that summing junction, and here we have one node, here we have one node, in addition to the input and output node. While there is some nodes which can be combined together. For example, these two summing junction actually can be merged or combined to be this, because they go to the same point or to the same node without any differences. Okay, so the main node here, which is the input, and the output nodes, here we have one summing junction, another summing junction, Here also we have summing junction. So after we identify the node location, we need to label this node. We put a name for each node like x1, x2, x3, and so on. Then we draw the connection or the interconnection between one node to other node to show the gain value or the transfer function of subsystem. For example, between this node and that node, we have G1S. This will be the gain value. Between this node and that node, we have J3. Between this node and that node, we have only one because there is no subsystem here. Between the output node and the feedback here of this node, we have J6S. And between the same output node and the node here, we have the value will be G8. And between this node and the input node here, which is the error value here, or the main input node, we have the value will be G5. So if you can see here, the representation for the signal flow graph will be like this one. So we have the input node, which is RS. We have this node, we call it X5. Then we have node of the second summing junction, we call it X4. And we have here another summing junction, we call it X2. Here we have the output node. And we can see how we represent the branches with their transfer function or gain value. And when you represent this transfer function or gain, you need to consider the sign of the feedback or the parallel path. So if it's negative, so you put it negative, like negative G6 here. You can see here in the previous figure for G6 it is G6, but here we have negative value, and here for example we have also negative value. So when we talk about G2, we will say also negative G2. You can see here this is negative G2. This one is positive G1, positive G3, positive G4, because here it's not the feedback, it is our parallel path. G3 and G4 are in parallel, not G4 is not a feedback for G3. You can see here this is same direction go forward, the same direction for G4 is go forward, and it's a parallel system. Then this is the overall signal flow graph of our control or block diagram for the control system. Actually, this signal flow graph, you can see here we have between x3 and x2 we have only the gain is 1. So when you have the gain is 1 and the 1 will be multiplied by the G7 or 1 will be multiplied G3, it will not affect the overall gain of the path, as we will see later on when we use the Mason's rule to simplify the signal flow graphs. There is another examples there is several other examples in the slides. You can refer to it to show how we can convert from block diagram into signal flow graph. Now we are going to talk about Mason's rule as a formula used to simplify the signal flow graph to represent the single transfer function of overall system. Previously, when we talk about the block diagram, we used the reduction techniques to simplify the complicated control system into a single block with a single transfer function. In this topic about the signal flow graph, the Mason's rule will be represent or will be used to represent the overall transfer function of the signal flow graph using using the Mason's formula. But before we go to learn how we are going to use the Mason's rule to simplify the signal flow graph, we need to highlight some definition or concept for the Mason's gain formula. The first one, we need to know what is the difference between input node and output node. So the input node here for this signal flow graph, the input node is the first or the only, it has only outgoing branches. So start from the input point, as we mentioned before in the previous example. When we say RS represents the input node. So the input node is only has outgoing branches. So for example, in this case, X1 represents the input node. Then the output node, it only has incoming branches. So it represents the output of our system. So Y2 in this signal flow graph represents the output node. We have also a path. Path is a branch of sequence from one node to another node to show the direction of the signal. So for example here, the path between X1 and Y2 here is go through Y1, X2, Y2. So the first path here in this signal flow graph is X1, y1 x2 y2. We call it the path from x1 y1 x2 y2. Okay, then another, we have also another path here, which is x1 y1 x2 y1, x1 y1 x2 y1, because we go here and go again into y1. Then we have another path which is x1 y2, so we go from the node x1 directly to the node y2. So this is the path. The path is a branch or sequence of branches that can be transferred from one node to another node. So we have two nodes, for example, between them there is a path which connect between these two nodes, either directly or indirect through some intermediate nodes. The forward path, this is the path. This is, as we mentioned here, we have three paths, but not all are forward, because we have this node path, which is the second path, x1 y1 x2, then again to y1. This is, it's not a forward path because it has a backward. But the first path, which is x1 y1 x2 y2, is a forward path, and also x1 and y2 is also another forward path. The forward path starts at the input node and ends at the output node, so it does not have a backward. It always go forward from the input to the output. Why we need to know these definitions? Because later on this definition will be used to construct the formula of the Mason formula to find the transfer function. Also, we need to know the loop. The loop is a closed path along which is no node is made twice. So you have one loop here. For example, here we have a loop which starts from y1, go to x2, again to y1. This we call it loop because it starts at the node y1 and stop at the node y1 again. So we call it this. We call it the loop. Also, non-touching loop. That means we have two loops but non-touching, so it does not touch each other, separate node or individual nodes. They do not have any nodes in common between them, so this we call it non-touching loops. Path gain, we already defined the path, and we said, for example, here we have several three paths actually, x1 y1 x2, and also x1 y1 2 x1 y2. All this we call it path. But when we say the path gain, that means it represents the product of all gain of the path. So we have, for example, between x1 y1 we have the gain is a1, between y1 x2 we have the gain is a2, between x2 and y2 we have the gain is a3. So this path has a gain of a1 times a2 times a3. For example, the other path, which is start from x1 go through this into y2, it has the gain of a5. So this we call it the gain path or the path gain. Then we have the forward path gain. So as we mentioned before, we have forward, we have backward. So the forward path gain is the path gain of the forward path. So we need to identify the forward path, then we calculate its forward gain. The loop gain represents the gain of the loop. For example, here in our here in this part, which is, we say this is the loop, correct? y1 x2 and again to y1. So what is the gain of this loop? We can see the gain is a2 times a4, a2 times a4. So this we call it the loop gain. So now we are going to talk about Mason's rule. What is Mason's rule? Actually, it is a formula which represents the overall transfer function of a complicated signal flow graph. Okay, so we have signal flow graph. We don't want to go for reduction techniques, so we convert the graph into block diagram, then go to reduction technique to find the transfer function. But we can directly use this formula to write the overall transfer function of our signal flow graph. So the formula said gs equal to output cs over input rs, which equal to summation of k for the forward path tk delta k over delta. Here we have the definition for each variable in this formula, and actually this formula is the same as like 1 over delta summation k bk delta k, both TK or PK represent the forward path of our signal flow graph, and the kth forward path actually, because we have k here. K represent the number of forward paths. We can see the definition here. K represent the number of forward paths. So if you have one path only, so the k equal to 1. If you have two paths, so k equal to 2. Three paths, so k equal to 3. Then we have tk here. It is the kth path. So we said the first forward path, the second forward path, the third forward path, and so on. Okay. The value here delta represent in this formula, which equal to 1 minus summation of loop gain. So we already mentioned what is the definition of loop and what is the definition of loop gain. So we need to find the summation of loop gain together, and we put them. We put 1 minus the summation of loop gain. Then this sign become plus summation of non-touching loop gains, taking 2 at the time. That means we are going to find any two loops which not touch with each other. So like two loops, a loop 1 not touch with loop 2, so the summation of their gain will be included in this formula here to find the value of that delta. If there is no non-touching loop, so the value of delta will be only 1 minus summation of loop gains. Then we have also minus summation of non-touching loop, taking 3 at a time, taking 4 at a time. We mean by taking 3, taking time, that means taking 2 means we are going to find any two loops which is not touching with each other. If we say 3, that means we are going to find 3 loops which is non-touching with each other. If 4, 4 loops which is non-touching with each other, and so on. Later on, we will see an example how to define these non-touching loops. Then delta k, which is here delta k, represent the value of delta with omitted or eliminated the loop which is touching the kth forward path. So for example, I am talking about the first forward path. The value of delta 1 will be the value of delta minus the value of the gain of loops which touch the first forward path. When I say delta 2, it is the value of delta minus the value of the gain which is touch the second forward path, and so on. We will see in the example how to apply these or how to find this parameter in order to formulate the Mason's rule and find the transfer function of the signal flow graph. Here we have the first example here. The example said apply Mason's rule to calculate the transfer function of the system represented by the following signal flow graph. So we have here signal flow graph, and we said always signal flow graph consists of nodes and branches. Okay, so we have nodes here which represent the signal, and we have branches which represent the system. So we have node R here, we have another node here, and between node R and this node is equal to 1, the gain is equal to 1. Between this node and that node, the gain is equal G1, G4. Between this node and that node, the gain is equal G2. Also, the gain is equal to G3. We have two, you can see the arrow here, the direction of arrow always forward. So both we can consider as a forward path when we find the forward path of this system. So the first, there is some step we need to follow in order to find the overall transfer function or the equivalent transfer function of this signal flow graph. The steps are, first we need to calculate the forward path gain, BK, for each forward path. Before we find the forward path gain here, we need to know how many forward paths do we have in our signal flow graph. Do we have one forward path, two forward paths, three forward paths, and so on? Then for each forward path, we are going to find the gain of this forward path. The next step, calculate all loop transfer functions. So we need to find the gain of the loops. So how many loops do we have? We have one loop. What is the gain of this loop? We have two loops. What is the gain? What are the gain of these two loops, and so on. Then we need to consider the non-touching loop 2 at the time, non-touching loop 3 at the time, and so on. After that, we are going to calculate the value of delta, then the value of delta 1, delta 2, delta 3 depends on the value of k. Okay. So here we have in this figure, if we go back again to the figure, actually we have loops forward path. Forward path, we said it starts from the input point or input node to the output node. So this is the input R, This is the output C. How many forward path do we have between these two nodes? Forward path means start in one direction forward. So if we see here, this is the first forward path, go through this point until this node. Again, this is also forward. Again, is forward, forward until we reach to the C. So this is the first forward path, which is B1 or T1. Okay, so this is the first forward path. We said forward, that means that's the direction of arrow in all part of this path is like this one, from input to the output, input to the output. Okay, the second forward path in this figure here, or in this signal flow graph, is also start. You must start from the input point and stop at the output point. Don't start from here or there or there. No, you should start from the first and at the end. So this is how to find the forward path. The second forward path, start from R also, go to this point in the same direction actually, and at this point it will go there, up, up again, back to the main direction here. So this we call it the second forward path, or we call it B2. Okay, someone say also we have here forward path. No, it is not forward. Why? Because the arrow direction here is backward. The arrow of this direction is backward, is not forward path. Okay, that means we have two forward path. After we know that we have two forward path, that means the value of k here is equal to 2. Now we need to know the gain of this forward path. What is the gain for the forward path number 1? What is the gain for the forward path number 2? The gain for the forward path number 1 represents the product of all transfer function or gain of all branches. So the forward path number 1 start from R, it has the gain of 1. So it will be 1 times G1 G4 times G3 times 1 times 1. So it will be G1, G4, G2, G1, G4, G2. So this will be the forward path number 1, the gain of the forward path number 1 of P1. For the gain of the forward path number 2, we said the forward path number 2 is the same, only the difference is here. So G2 will be replaced by G3. So it will be like G1, G4, and G3. Then we have here 1, 1. When you multiply by 1, so the gain not change. So this is the forward path gain of number 1. If you go to the formula here, that means we already have this one. This value already there, BK or TK. This value is represent, when we say the summation of BK or TK here, it will be the summation of the gain of P1 plus B2 in our example here. It will be multiplied by delta 1, because we need the summation of BK delta K. So it will be delta 1 P1, delta 2 B2. Then all these value will be divided by delta. Okay. Now we already have B1, we already have B2, which represent the gain of the forward path number 1, the gain of the forward path number 2. We need to find more about delta 1, delta 2, and delta. And in order to find delta, we need to find the loop gain, because delta is equal to 1 minus loop gain. Then we need to find non-touching loop 2 at times, 3 at times, and so on. After we find this delta, we can find the value of delta 1, which is here, equal to delta minus the value of the loop gains in terms of the kth number of forward path. Okay, so we back to our example here. We already find B1, B2, and our transfer function will take this form. It will be CS over RS equal to P1 delta 1, P2 delta 2 over delta, and B1 is equal to this value G1, G2, G4, and B2 will equal to this value G1, G3, G4. So here, this already B1 is here, and this is B2 will be here. Okay. Now we need to find the other three variables, which is delta 1, delta 2, and delta. And we said in order to find delta, we need to find the loops and the loops gain. So here in our figure, how many loops do we have? We said the loop, you start at one node, you end at the same node. Okay, so in the same direction actually. So we have here, I cannot say this one is the loop. Wait, just remove this. Okay, I cannot say this G2 and G3 represent a loop because they are in parallel, they are go forward, it's not a backward. The loop is you start at one node, you go forward, then you go backward to the same node. So here we have one loop, this is one loop, start from this node, go to that node, again return. And the gain of this loop represents the product of gain of the branches of this loop. So we have G1, G4 times H1. Since H1 here is positive, just keep it G1, G4, H1. This is, we call it like loop number 1. Okay. So if we say this one is loop number 1, this is loop number 1. Okay. Now we need to find the other, is there any other loop in our signal flow graph? Yes, there is some other loops here. To remove this, you can see here in this loop, you can see the loop here. If we start from this point, go there, forward, 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 then we have a backward here. So we start at this node, we return to the same node. We start at the node here and we return to the same node and this direction. You see, in the same direction. We start at node, end at node in the same direction. So with this, we call it loop number 2. Why this is not loop? Because we said the arrow here direction in opposite ways. No, we cannot say it's go there because this is arrow is opposite to that arrow. So for the loop should be closed loop, start from one node, end at the same node. So we have two loops here, and the gain of the two loops can be found by the multiplication of the, or the product of the gain of the branches of the loop. So for the first loop here, L1, the gain is G1, G4, H1. For the second loop, which is L2, the gain is G1, G4, G2, and negative H2. Do we have other loop? Yes, we have another loop. We have the third loop here, which goes through this point, go through G3, again return back to this point. So the third loop here, which is L3, will start from the same node, but it will go through the other branch, which is J3 here, and it will return to the same. So the gain here will be G1, G4, G3, negative H2. So you can see here, these are the three loops that we have. Loop number 1, which is G1, G4, H1. Loop number 2, negative G1, G2, G4, H2. Loop number 3, it is the same as number 2, only the difference with the value of the G2 here instead of G3 there. Okay, because they are common, they have common nodes. Okay, so this is the loop or the gain of the loop. Where we can use these values or this gain, we are going to use them in the formula of the delta. You can see here the formula of the delta here. It says summation of loop gains. So the delta value will be 1 minus the summation of this loop gain, which is G1, G2, G4, and so on. Okay, so this L1, L2, L3 will be substituted in the formula of finding the value of delta. So the value of delta here will be delta 1 minus summation of all individual loop gains. Do we have any non-touching loop? I mean, is loop 1, is loop 1, this is loop 1, is loop 1 touch loop 2? Is there any common node between loop 1 and loop 2? Yes, because loop 1 and loop 2, they have this node in common, this node in common. So that means they are not non-touching loop, they are a touching loop. Is loop 1 non-touching with loop 3, which is go through this way? No, because they have also the same. They have this node and this node in common. Is loop 3 non-touching with loop 2? No. They are also touch each other. They are touching each other at this node, that node, that node, that node, and so on. So we do not have any non-touching loop. Since we do not have any non-touching loop, so this part of the formula here, this part of the formula actually will be omitted. From here, non-touching loop, we do not have non-touching loop. So this part will be omitted, this part also will be omitted, and so on. Our formula of delta will be delta will equal to 1 minus summation of gains for loop. Gains for loop only this part. The formula of delta will be this part. Okay, so if we refer here to our the solution of the example here, the value of delta will be delta equal to 1 minus summation of individual loop gains only. There is no non-touching loop. This is the formula. Then you substitute for the value of L1, L2, L3 by their gains, which is G1, G4, H1, negative G1, G2, H2, and so on. Now, this delta already known. We already know the value of delta. We still need to find delta 1 and delta 2. How to find delta 1 and delta 2? Based on the formula, we need to find the value of delta, then we exclude or we eliminate the value of loops which touch the forward path, the case forward path. So what is the case forward path here? You can see here, we said we have two forward paths, which is 1 and so in order to find delta 1 and delta 2, delta 1 is related to the forward path number 1, delta 2 is related to the forward path number 2. We need to omit any loops which touch with the forward path from the formula of delta. So for example, for the first forward path, it start from R, we said it's go through the forward path until the end, which is C. So this is the first forward path, which is P1. So do we have any loops which is non-touching with the forward path here? We said we have L1, this is the first loop, L2 is the second loop, L3 is the third loop, which is the big L3, means this one go there and also return to this point. Okay, so we have the three loops here, but the three loops are touching the forward path number 1. So there is no non-touching loop with the forward path. Since the three loops are touching the forward path number 1, that means the value of delta 1 will equal to 1 only, because delta is equal to 1 minus, here can see delta is equal to 1 minus loop gains, and all these loop gains actually already touch the forward path. So this loop gain here we have delta minus summation of loop gains, so these loop gains will go with that loop gains. We still have the value of delta 1 is equal to 1 only. Okay, since there is no loops which non-touching with the forward path, so the value of delta 1 will equal to 1. Okay, for the delta 2 is related to forward path number 2. So the forward path number 2 is start from R, go to this point, again go through G3, again to the output. So for the forward path number 2, which is P2, also it touched with loop number 1, it touched with loop number 2, it touched with the loop number 3. So since it touched with all loops here, so the value of delta 2 also will be equal to 1, because all the loops which touch the forward path will be omitted from the value of delta here. So since it is omitted, it will only stay the value of 1. We only have the value of 1 from delta only. Okay, so delta 1 and delta 2 will equal to 1 here. In both cases, delta 1 is equal to 1, delta 2 is equal to 2. I mean delta 2 is equal to 1. So you can see here from this formula, we already have B1, which is here, delta 1, which equal to 1, B2 is here, delta 2, which equal to 1, and delta, which is here. So we just substitute for all these value in this formula to get the transfer function, which is Cs over Rs here. So the overall transfer function of our system will be G1 G4 times G2 G3 over 1 minus G1 G4 H1 G1 G2 G4 H2 G1 G3 G4 H2. So this will be the transfer function of our signal flow graph that's showing in this figure. Okay, in order to know how to find the touching loop, and I mean the non-touching loop, and how to include this non-touching loop in our formula of the Mason's rule, we have another example here, and this example will show you how to find the non-touching loop to taken two at times. And also there is another example in the slide, you can refer to it to find for three non-touching loop at times. Okay, so here apply the Mason's rule to calculate the transfer function of the system represented by the following signal flow graph. So we have this signal flow graph, and it consists from several nodes with several branches here. We need to use the Mason's rule to write the transfer function, the overall transfer function that relate between the output of our system ys and the input of our system, which is rs. That means always transfer function is equal to output over input. So how to write the transfer function here, which is ys over rs? We need to use Mason's rule. Okay, so in order to use Mason's rule, we need to apply the steps that we learned before. The first, we need to know how many forward paths do we have here in this figure. Forward path, that means the path which start at the input point and at the output. So this is the input point. This is the first forward path. Go here, there, there, and again go to ys. Okay. I cannot say this one is forward because this is backward. Also, I cannot say this is forward because this is backward. So this is the first part, which is P1. Then the second path here, which start from the input point and at the output point, is start from RS, go through G5, G6, G7, G8, and to the output. So this will be the forward path number 2. So we only have two forward paths. We do not have another forward path because this path is backward, this path is for backward. Okay, since we have P1 and B2, then we need to know that K is equal to only 2. We only have two uh, forward paths, so K is equal to 2. So our formula will be P1 delta 1 plus P2 delta 2 over delta. Okay, we need to define now what is P1, what is P2, what is delta 1, what is delta 2, and what is the value of delta. In order to find the P1, P2, we need to know the gain of the forward path number 1 and the gain of the forward path number 2. The gain of forward path number 1 is, if we go here, this is forward path number 1. The gain is the product of all gains of the path. So here we have G1 times G2 times G3 times G4. So this will be the B1. For B2 will be G5, G6, G7, G8. You can see here. So the path number 1 is G1, G2, G3, G4. B2 will be G5, G6, G7, G8. So this will be represent the gain of the forward path number 1 and forward path number 2. We know P1, P2. We need to know delta, and we need to know delta 1 and delta 2. We cannot actually here, before we know delta, we need to find, do we have any loops? Do we have any non-touching loop 2 at times? Do we have any non-touching loop 3 at times, and so on? So if we back to our graph here, how many loops do we have here? Actually, we have 4 loops. We have L1, start from this point back to the same point. So this loop number 1, and its gain is equal to G2 times H2. Then the second loop, which is L2 here, is start from this node, go forward, backward to the same node. So its gain is equal to G3 times H3. The third loop is start from this point or this node, go forward one, backward here to the same node. So its gain is equal to G6 times H6. Okay, so this is the loop number 3. The fourth loop will be loop number 4. Start from this point, go forward, then again backward to the same node. So its gain will be G7 times H7. Okay, we cannot say this big here is a loop. We cannot say this is a loop. Why? Because we start at this point, go there, and stop here. We do not back. If the arrow direction is back, so we can say this is a gain. But here you see the direction of arrow is forward, it's not backward. So we cannot say this area represent any gain for our signal program. So we have only 4 loops. Okay, since we have 4 loops, we already defined their loop gains. So we said L1 is equal to G2H2, L2 is equal to G3H3, L3 is equal to G6H6, L4 equal to G7H7. Now we need to find or consider 2 non-touching loops. Do we have any 2 loops non-touching with each other? If we just remove this one, okay, we can see here, we said we have how many loops? We have 4 loops, L1, L2, L3, and L4, and we know the gain for each loop. Now, is loop 1 touching with loop 2? That means, is there any common nodes between L1 and L2? Yes, this node is common between these 2 nodes. This node is common between L1 and L2. That means L1 is touching with L2. We cannot say they are non-touching. Okay, is L3 touching with L4? Yes, because there is one node in common between them. So L3 is touching with L4. But we have L1 is non-touching with L3 because L1 only use these 2 nodes. L3 use 2 different nodes. So there is non-touching loop. So L1 is non-touching with L3. Also L1 is non-touching with L4. So we have 2 non-touching loop considering 2 at times. So L1 non-touching with L3, L1 here is non-touching with L3, L1 is non-touching with L4. So we have L1, L3, L1, L4. Also L2 is non-touching with L3, L2 is non-touching with L4. So we have here L2, L3, and L2, L4. Okay, so we have 4 loops, each 2 non-touching with each other. Okay, so in this case, that means the point here that we have in the formula of the delta, which is non-touching loop gain taking 2 at times, it's there. So this term here will be included in the formula of calculating delta in this example, since we have 2 non-touching loop with each other, which is L1, L3, L1, L4, L2, L4, L3, L4. And we need to know what is the gain of this L1, L3. If you go to the figure here, L1, L3 means G2, H2 times G6, H6. Okay? But in the formula said the summation of L2, L3, L4, and L6 here. I mean L2, L3, L1, L3, L2, L4, L1, L4, and L2, L3. Okay, so we have 2 non-touching loop to each other. So do we have any 3 non-touching loop here? We do not have 3 non-touching loop. Why? Because L1 is non-touching with these 2, but it's touched with the 4th one. So we do not have 3 non-touching loop. L2 is non-touching with these 2, but it's touched with that one. L4 is non-touching with these 2, but it's touched with this L3 and so on. Okay, so we do not have 3 non-touching loop by considering 3 at times. So that means the formula of delta will stop at the 2 only. So when we calculate the value of delta here, delta is equal to 1 minus summation of loop gains, which is L1, L2, L3, L4, L1 plus L2 plus L3 plus L4. This is the summation of the 4 loop plus, you can see the formula here of delta here, the main formula. It shows that the main formula said 1 minus loop gains. Now the loop gains here is L1 plus L2 plus L3 plus L4. Then plus summation of non-touching loop gains taking 2 at the time. This will be the second term of our delta in our example here. So we can see in the example, this represent the value of delta. Delta is equal to 1 minus summation of loop gains plus summation of loop gains considering two non-touching loop at times. So we have L1, L3, L1, L4, L2, L3, L2, L4. So we just need to substitute for the value of the gain for these loops. So the gain of loop 1 here is equal to G2, H2, this one G3, H3, this one G7, H7, G6, H6. So we need to substitute in this term. And here L1, L3, that means we have the value of the gain of L1 times the value of the gain of L3. L1 is G2, H2 times G6, H6 here. Same. Okay, then G2, H2, G7, H7, H3, G3, G6, H6, and so on. So we need to substitute for the value of L1, L2, L1, L4, L2, L3, L2, L4. So this is the value of delta now. Now we find the value of delta. We have the value of P1, we have the value of B2, we have the value of delta. We need to find the value of delta 1 and delta 2 in this formula here. So in this formula of the transfer function here, B1 already there, B2 already there, delta already there. We need to find delta 1 and delta 2. And we said previously, if we want to find delta 1 and delta 2, we need to consider the gains which is non-touching with the forward path number 1 and the gain which is non-touching with the forward path number 2 in this example, because we have two forward paths. So we need, in order to find delta 1, we need to find the gain of the loops which is non-touching forward path number 1. In order to find the delta 2, we need to find the loop which is non-touching with the forward path number 2. Okay, so by eliminating here for the forward path number 1, this is the forward path number 1. Actually, go there, go on, I mean G2, G2, G3, and J4 and output. What are the paths or what are the loops which is non-touching with this forward path? L1 is touching, L2 is touching, so it will be ignored. We need to consider L3 or 4 because L3, L4 are non-touching with the forward path number 1. So here the value of delta 1 will equal to 1 minus summation of L3 plus L4. Why L3, L4? Because L3, L4 are non-touching with the forward path number 1. Okay, so this will be the delta 1. In order to find for, then we substitute the value of L3, L4. L3 is equal to G6, H6. L4 is J7, H7. We just put delta 1 is equal to 1 minus G6, H6, G7, H7. Then, in order to find the value of delta 2, we need to eliminate the forward path number 2 here, and we find which loops are non-touching with forward number 2. So this is the path, forward path number 2, start from RS, go here G5, G6, G7, and again to YS. Okay, what are the loops which is non-touching with this forward path? So the loop are L1 and L2. So their value will be here. Delta 2 will equal to 1 minus L1 plus L2. We substitute for the value of L1, which is G2H2, the value of L2, which is G3H3. So this will be the value of H or delta 2, and this is the value of delta 1. Then we substitute these values in this formula. B1 is already here. Sorry. B1 is already here. This is B1, which is G1, G2, G3, G4. B2 is G5, G6, G7, G8. Then we have the value of delta 1, which is 1 minus G6, H6, G7, H7. Value of delta 2, we substitute here. And then the value of delta, which is here. This is the value of delta, which represents here. Now this will be the transfer function of our signal flow graph. And as you can see here, It's one transfer function for this complicated control system, which consists of 7 transfer function or 8 transfer function. Actually, there is more example in the slides. You can refer to it and some exercise. So you can try to solve this exercise, which is available in the slide of chapter 3. Thank you.